In this lecture, we will deal with punching shear. We will begin by answering the question, what is punching shear? We will then go on to look at how the punching shear resistance of a reinforced concrete element can be assessed. And finally, we will discuss some measures which are available to the designer which will increase the punching shear resistance of such an element. What is punching shear? Punching shear is a brittle failure mode. It occurs when a concentrated load is applied to a surface and gets its name from the fact that the concentrated load is in effect trying to punch a hole through the surface with which it is in contact. In reinforced concrete, the two most common instances where punching shear arises and needs to be addressed in design is in the column to slab connection in a flat slab and in the column to foundation connection in a typical concrete pad foundation. In both these cases, the punching shear arises from the fact that the reaction to the loads is provided over a small surface area, namely the cross-sectional area of the column, which is the contact area between the two elements in question. In flat slabs, the punching shear at the column-slab interface results from the loading the slab imparts onto the column. In a pad foundation, punching shear occurs from the reaction of the soil on the underside of the foundation. In both these cases, the column merely provides the reaction to these applied loads. It is the fact that this reaction is applied over the relatively small surface area of the column cross-section that results in punching shear occurring. Punching shear failure is a sudden and catastrophic failure type. It occurs when the shearing stresses around the loaded area result in the formation of diagonal tension cracks, which in turn results in the formation of a diagonal fracture plane. Visual evidence of imminent punching shear failure in flat slabs is provided by the appearance of radial cracks on the surface of the slab around the column. After failure, only a truncated cone of concrete remains attached to the slab. A simple experiment showing how a greater area reduces stress can be carried out using a normal everyday pen. Place the top of the pen face down onto the table. Now, put your hand on top of the pen and press down. Notice the pain you feel in the palm of your hand. Next, turn the pen upside down and place your hand on the cap. Notice the increase in pain compared to the first test. The pain in your palm is directly related to the stress in the slab. The smaller the area over which the force can act, the greater the applied shear stress. At around 3 a.m. on the 20th of March 1997, the top floor section of a car park weighing 120 tons collapsed in Wolverhampton, England. The use of low-quality concrete and poor construction methods resulted in variations in slab depth and unacceptable cover requirements for the top and bottom steel reinforcement. Freeze-thaw action and poor waterproofing allowed water to seep into the concrete and caused corrosion of the reinforcement due to carbonation. The combination of reduced slab depth and loss of steel to concrete bonds brought about a column to fail in punching shear, which sparked 8 other columns supporting the floor slab to fail in a similar manner. Thankfully, despite being open at the time, the car park was empty. However, the damage was so great that the entire car park had to be knocked and rebuilt, resulting in much disruption to the city. These images are a good example of the diagonal cracking and truncated cone-shaped failures common to punching shear failures, as previously discussed. In this section, we will look at how a designer may assess whether punching shear failure is an issue in the element they are designing. For the purpose of this section, we will examine the case of a flat slab supported by a column. However, the basic principles could just as easily be applied to other scenarios, including that of a column supported by a pad footing. The methodology for assessing the punching shear resistance of a slab involves examining a series of perimeters, each located at fixed distances from the column face. At each individual perimeter, the shearing stresses due to the punching is calculated and compared to an allowable shear stress. These perimeters are referred to as control perimeters and are denoted by the letter U. While this calculation can be performed for perimeters at any given distance from the column face, there are a couple of perimeters which are of critical importance and must be assessed. The first of these perimeters is at the column perimeter, which is located at the column face itself. The second perimeter of critical importance is the critical control perimeter. This is defined as the perimeter located at a distance of 2 times the effective depth of the slab from the column face. Ultimately, this is the perimeter which will determine whether we need to provide punching shear reinforcement in the slab or not. Here we will look at how to calculate the shear stress at any perimeter around a column supporting a flat slab. In its most simple form, the shear stress is calculated by dividing the shear force applied by the area to be sheared. There are a couple of important points to note when applying this principle to punching shear stress in flat slabs. The first point to note is that the shear stress applied, VED, is in fact the reaction at the column from the slab being supported. This shear stress, or reaction, must be increased by a factor beta, which accounts for the increase in shear stresses around the column due to the hogging moment. The area to be sheared at any perimeter is simply the effective depth of the tension reinforcement times the length of the perimeter under consideration. Here it is important to note that the effective depth of the top reinforcement is the mean depth of the 2 layers of reinforcement over the column. All columns will experience hogging moments from uneven loading on either side, resulting in uneven shear distribution. The eccentricity factor beta in the formula for applied shear stress accounts for the uneven distribution of shear at the column. For most structures, typical values for beta can be used. The values in Eurocode for a corner, edge, and internal column are shown here. The column perimeter is the first perimeter we check when assessing the punching shear resistance of a flat slab. As the name suggests, the column perimeter is located at the face of the column. The area over which the applied shear is distributed in the column perimeter is equal to the length of the perimeter, U0, times the effective depth of tension reinforcement, D. As with any punching shear check, at the column perimeter, what the designer wishes to do is ensure that the applied shear stress is less than the allowable shear stress. In order to calculate the design shear stress at the U0 perimeter, we simply divide the applied shear force times the factor accounting for eccentricity by the area to be sheared. In the case of the U0 perimeter, this area is simply the length of the perimeter, U0, times the effective depth of the tension reinforcement. Again, it is important to note that the effective depth of the tension reinforcement is the mean effective depth of the 2 layers of steel passing over the column head. Once the applied shear stress at the column perimeter has been calculated, the designer must ensure that it is less than the shear stress capacity or resistance at this perimeter. This is calculated by first calculating V or D max, as shown in the formula here. It is worth noting that V or D max depends only on the compressive strength of the concrete in the slab. Therefore, should the shear stress capacity be insufficient at the column perimeter, there is no means of increasing this capacity without increasing the size of the column, increasing the depth of the slab, or increasing the strength of the concrete. Consequently, failure at the column perimeter cannot be resolved by providing additional reinforcement, either in the form of additional tension reinforcement over the column head or shear links. Once a designer is satisfied that there is sufficient punching shear resistance at the column perimeter, they may proceed to check the shear resistance at the basic control perimeter, U1. The first step in checking the basic control perimeter is to establish the length of this perimeter. The basic control perimeter is located at a distance of 2d from the face of the column. Once again, this d dimension is the average or mean effective depth of the main tension reinforcement over the column. It is also important to note that U1 is calculated with rounded edges. Again, these edges are taken as having a radius of 2d from the corner of the column under consideration. Again, at the column perimeter U1, the designer wishes to ensure that the applied shear stress, VED-U1, does not exceed the punching shear resistance at this perimeter. The applied shear stress is calculated in the same way as it was calculated for the column perimeter. However, now, the perimeter has been increased from the column perimeter to the U1 perimeter. Therefore, the applied shear stress at the control perimeter will be less than the applied shear stress at the column perimeter. However, the punching shear resistance at the control perimeter is now VRDC as opposed to VRD max. VRDC is calculated from the formula shown here. The important thing to note about this formula is that it depends not only on the strength of the concrete, FCK, but also on rho L, which is the ratio of the amount of tension reinforcement in the orthogonal layers at the top of the slab over the column. Rho Lx and rho Ly are the mean ratios of reinforcement in the x and y direction over the column in the flat slab. To be considered, the reinforcement used to calculate AS must extend at least a column dimension plus 3D on either side of the column. Typically, rho Lx and rho Ly are calculated on the basis of a 1 meter wide strip of reinforcement. Therefore, BW is typically taken as 1000 millimeters, while ASXL and ASYL are taken as the area of reinforcement per meter width of the range under consideration. If it is established that the punching shear stress at the basic control perimeter is less than the punching shear resistance at the perimeter, then the designer has shown the slab has sufficient punching shear resistance and no further checks are necessary. However, if the applied shear stress exceeds the shear resistance at the basic control perimeter, the slab has insufficient punching shear resistance and the designer has further work to do. Additional measures can be considered in order to increase the punching shear resistance of the slab. The first of these measures is to try and increase the reinforcement ratio by increasing the amount of tension reinforcement over the column. However, as we have seen on the previous slide, the value of the reinforcement ratio ρ is limited, meaning there is only a certain amount of additional punching shear resistance that can be attained using this method. Later, we will go on to look at some other means by which the punching shear resistance of a flat slab can be increased. As it can be tricky to calculate the control perimeter of some columns, the Eurocode defines these perimeters for us. Shown here are the methods for calculating U1 for an edge and corner column. Note how the perimeter is not quite the full extent around the column. Openings in slabs for services or other reasons need to be taken into account when calculating the control perimeter. Openings up to 6D away from the column face need to be accounted for, as they influence the length of the control perimeter, and hence the area over which the shear force is dissipated. The Eurocodes also provides guidance for this, which can be seen here. We will now look at some options available to the designer to resist punching shear. There are numerous methods to increase the punching shear resistance of a concrete section, namely, increasing the slab depth, which in turn increases the area over which the shear force is distributed, providing shear reinforcement, however it should be noted that there is a limit on the resistance from additional top steel, providing shear links, which is inexpensive but requires strict quality control on site, the construction of a column head or drop panel, and the introduction of a proprietary system such as shear studs. Column heads or drop panels work in a similar fashion to increasing the slab depth, but are far more economical. They work on the principle of increasing the area over which the stress can be distributed. Drop panels provide a greater D value and increase the control perimeter. There are two types of column heads and drop panels, standard and enlarged. For the standard measures, punching shear must only be checked outside the column head. However, for the enlarged measures, punching shear must be checked outside and within the column head. Proprietary systems are the most common form of punching shear resistance due to their quick and easy installation. Examples of a shear stud proprietary system are shown here. Having completed this lecture, Let's examine what we have learned. We now know how to define punching shear, assess if punching shear is an issue in a particular slab, and overcome punching shear using a variety of alternative methods.